Now we get to the gravity analysis. Here you can see I show you how I came up with my graphic for analyzing the gravity. The blue is Earth gravity and the red is the moon gravity. You can see an obvious difference. The moon objects fall slower while the blue objects fall faster. We won't see those animated in the analysis. I'm just showing you how this graphic was generated. The footage was matched up to the astronauts so that the astronauts were the same size, and based on that the analysis was generated. You should familiarize yourself with the number on the graphic. They represent frames. The object should take a certain specific number of frames to fall every time. There is no exception. Gravity does not change. And because of the frames per second, 24 frames per second here presented at 30 frames per second, it's the same thing. It's 1 second of their time. And you can tell by the sound sync. It's 30 frames per second. You can tell by how many frames it could take an object to fall on the moon in a certain number of frames and a certain distance. It doesn't change. So here we have astronauts jumping for various reasons. Locomotion, fun, who knows? There obviously was no jumping in the first three that I could locate, and mostly in A17 here. And of course they had the astronauts on wires, so in my analysis their gravity was always accurate to the moon. This was a frames per second combo with wires, and based on the equations you saw earlier, about 46% of the weight staying up on wires, and so it was quite the same as the wire simulation. Weightless quality, or lowered weight quality. But of course combined with the frames per second, which was 44, they always fell at the exact right speed. Here we monitor at the top of the head because no matter what part of the astronaut you look at, as long as you can clearly designate where it is, at the beginning and ending of the jump. Here also taking the beginning of the jump to the apex where it stops going up, or the apex down where it starts going down, to where he lands. If you question my choice of these, then there's not much I can do about that. But I was as accurate as I could be. You can see I matched up the astronaut to the graphic based on where the feet were located. And if they were leaning forward at the top of the pack, it's where the top is. And if you see them leaning over, that is very accurate. The pack doesn't really go much over that, the astronaut's head. And based on where the astronaut is located in the suit, eye level about middle of the visor, and the head was not much over that. I determined what the height was. And so of course, these are all wrong in my factor change clips. But not if you include wire work. And here of course, they're right every time. What it does do is it should provide confidence in my method here. Also, I think one earlier on was yellow. That meant it was off by a frame. I could only find one other occasion where I think my analysis was off by a frame. But because of all of their little tricks with frames per second, dropping frames and so forth, I can see why that might be the case. Sometimes I establish the footage. You can see up in the top left corner a reference of the actual footage, and then how I modified the footage you can determine based on the differences. Now getting to the dropped and thrown objects, there's quite a few. This is really one of the significant things that led me to proceed forward with this analysis, is that we found so many opportunities to measure the gravity. You just saw the classic hammer and feather, and that was one of many. Several dozen here. And they littered the moon, literally, in the last few missions. And there were quite a few opportunities because they were walking around on wires, running around on wires, and acting very comfortable on the moon, where it's a pretty dangerous environment. So obviously I didn't analyze all of these. They're not always really analyzable. You can, I'll show you, after the presentation of these clips, you'll see which ones dissolve away as yellow. Those are the ones I did not include, and as you can take a closer look at this for yourself and see if you'll find something different. And here we go. We shall eliminate the ones I cannot analyze. We're left with quite a few that I can, and those are significant. Even the ones being wrong should raise alarms. We have a bunch. This is wrong. It says it takes 19 frames in the footage. Here you go, side by side. And you can see the modified one. Definitely falls slower, as it should on the moon. And here is my factor of 5 to 4 slowed down, here. And it is correct. You can always repeat these. Pause, replay if you want to see it again. I only show them to make the difference clear. It was 22 in the footage, I modified it to make it 30. Here you see them side by side, here are some of the earlier. It's Apollo 14. You can see the incredible distortion in the footage. It's really incredible how they tried to hide. The footage itself is also unbearable to look at in slow motion, the presented speed. But at this even makes it worse. So it's 21 in the raw footage here, 31 in the modified is correct. See the difference? It should be 31 at that height. There's quite a bit of difference of 10 frames, so we're not talking a frame or two here. And in my footage it is 12, which is correct. I say my footage, my modified version of the footage, based on the frames per second factor. 21, 30. You can see the difference, how slow it takes, how much longer it takes, and in my footage it is longer and slower. Some of these are considered questionable, but it always plays out. It's correct in mine. It's way off on the moon, the NASA footage, and I modified. And you can see the difference. So I'm just running through these again and again and again. It just keeps going on, and you can look at these more closely. I just wanted to present them to you so that you can do more careful analysis of my analysis, which you should do. I would like to spend some time to confirm what I have discovered here. Here is an astronaut, and then I move the graph. The measurement graph to where the action indicator bars are. When the frames hit, you can see it turn red if you didn't already notice. And it gives you a reference, the same size as my astronaut graphic. I just moved it separately so that the astronaut graph is there to establish an accurate sizing for measurement, and the overlay graphic is moved to more accurately show the distance the object traveled in frames. Every time it's about 2/3 difference there. It's 2/3 as many frames as it should be. And in mine, correct every time. Well, let me correct that statement. Almost every time. And I'll show you why soon. Those are not correct. These are some tricky fellows who created this footage. This is quite extraordinary, looking at it now. I missed that one. Yellow 15 was off. That's minor, it's not really an issue as discussed. It's frame dropping. They had all kinds of tricks going on to disguise what was happening here. When you see the yellow graph there, it just means that I've done some stabilization, and I put it there as a reference. It was usually hand-done stabilization, enough that you can measure. Here you can see the lens distortion, fairly obviously because of the stabilizing. And here you can see how the same objects in the background get distorted as they approach the edge of the frame. Now these are, the past one and this one are, really extraordinary things. What's happening here is that it's wrong in my footage. And it was like, why is that? Well, I realized that they did a frame adjustment. Notice the factor change at the bottom. 0.41, it was 0.54, 0.41, back to 0.54. They changed the factor during the throw. The object movement to simulate the moon, the proper speed, and it jumped back, and you can't tell. They may not be doing these for this. There's a whole section on speeds change. You can see how often they use that technique to disguise their methods. Again, you can see the factor change. This is a harder one because the camera is moving so much, but it's clear to me. You can see that I have multiple versions of the graph. One is in the background. You can see I have two moon men, astronauts, because I'm trying to measure how far it went. I do the factor change and it works. 0.41. Why 0.41? Because that's your film and normal speed, and you have to multiply that film speed, the length, by 0.41 to achieve simulated moon gravity. Now these points were in the analysis presentation. Now this is wrong. Watch the 0.4 change. 0.5, there it is. And then change back. Here it is. It's going to happen again. 0.41. Unless you're looking at the bottom, you won't notice these changes. They found because they could do them. Obviously they did. They didn't do it every time. So that's when I found it was wrong. Look at all the movement taking place. Look at the factor change timing. And it's amazing that it works so well. He's running at us in slow motion, and there's a speed change right in the middle. You can see extreme popping and mucking up of the footage. Here's the classic event. Now we get to the sand. Basically, when I did my analysis, I looked through all the footage several times, and anytime I found sand falling, I marked it, separated it out as a clip. So here's what we're seeing every time I found sand falling. Now when I do the analysis, you'll see I limited it to the ones I could, though I could analyze. Because of the mucking of the image, especially sand separates. Unless you get a closer indication of when it starts and stops, going up or going down, you really can't analyze it. Sometimes you can, you don't need where it stops. You just need enough frames so that you can say, I've seen it move. And again, as we get further emissions, A17, almost the case, it has more. A16 and A17 are almost always the jewels of the missions for analyzing footage. Here's our graph astronaut for measuring, and here you saw the sand falling. It's wrong, I say 31 frames. I'm showing you clearly where it begins. Where it ends, it should take 40 frames. Now I am confident in my discerning where the sand starts to fall and when the front edge hits the ground. And it is correct in my footage. It is very blurry, very difficult. I would go back and forth and see the changes on the ground, and wherever I did, I discerned where the sand hit, even if it's totally off a frame or two. That's minor compared to the differences we're seeing here. Watch closely. Compare the different rates at which the sand is falling in these images. It is easy to see that this footage that NASA presented to us was in fact slowed down, and then sped back up again to match the gravity on the lunar surface. And when corrected, you can see that the sand is actually falling in Earth's gravity, as shown in these examples. Watch as this astronaut drops the sand from the shovel that he is trying to get into the sample bag. Notice the difference in the astronaut sidestepping in the left frame versus the right frame. You cannot have that happen in lunar gravity. This was clearly filmed on the Earth. Here you can see the difference when I stopped before it hit the ground. I couldn't read clear when it hit the ground, but you can clearly analyze at any point during the fall if you want, so I stopped here. The rate is the same on those frames. I encourage you to do your own analysis of these two frames and the ones that will follow. What you will find will be very interesting indeed. In these frames, watch the difference at the speed of which the sand falls. You'll notice that the sand in the left frame hits the surface first before the sand in the right. Again, please notice the clip. It's right next to the bottom. You can go to the NASA site referenced earlier in this presentation and look at the evidence for yourself and determine for yourself what's going on in the footage. Try to keep a mental note of how many times you are seeing things fall in this clip. Note the different rates at which the sand falls on the left compared to the right, and then back to the middle. And then back to the left and back to the right, and then back to the middle. The sand behaves as if it was in Earth gravity, slowed down and then sped up again, and then slowed down. Do you realize how many times we're seeing things fall here and the wrong speed in the NASA footage? This is not a fluke. This is clear evidence this imagery is faked. This is an interesting dilemma. I had to determine where the top of the instrument was. And then, to help aid myself with the analysis, I used one of my gravity balls. And you can see it matches up. It doesn't match up, according to my analysis, in the expected times. And here are a few examples of an astronaut falling down, kicking up sand. And here, scooping and tossing sand with a shovel. Here I use the top of the sand. Here it hits the top and falls. You can see it disappear, and it's a great time to determine when it starts and stops falling. Let's compare a couple of these clips. He did a lot of shoveling, so I have a lot of opportunities to measure. It's wrong every time. To demonstrate this, I will speed the footage up, slow it down, and then speed it up again to match what was actually happening. And as you can see, NASA got it wrong again. Let's watch that example one more time. Keep an eye on the top counter as the sand hits the ground. You'll notice that the time frames are different. This would not be possible had this really been on the lunar surface. This time, we see the astronaut step backwards as he finishes shoveling. You can clearly see that one pile of sand is hitting the lunar surface, or so-called lunar surface first, before the other. Let us take a further look at how gravity affects objects that are thrown. And of course, they did the same thing that they did with falling objects. Whenever they could, they did a speed change event. Factor change to frames per second change to hide that this was faked footage. There's only a few of those. I find those very interesting, where the astronaut's jumping. At the same time, sand is falling, and you can clearly see that the sand falls faster. This is the moon speed that NASA, aka NASA imagery, has been presented to us. Look at the way the sand is and how it hits the ground before the astronaut does. They should be falling at the exact same speed. That's what the hammer and the feather was all about. It doesn't matter what object you drop from the same height, they land at the same time because there's no atmosphere to slow them down, slowing down the more air-resistant objects. So here, the sand is up with his feet, and it totally clears out below him, and then he lands. In all of these examples, the sand will always land first before the astronaut touches the ground. And here are a few more clips slowed down. This is the famous jump salute. And they're the more obvious ones to me. Sand is up there with his feet. Sand is up there with his foot, and then it's clear it's falling as fast as in Earth gravity. He's falling slower because he's hanging from a wire. The sand falls faster while the astronaut is clearly, again, hanging from a wire. It really makes me wonder how NASA was able to get away with this. Here we will go through some speed change events. These were when the film factor or frames per second at their end was changed midstream. When we're looking at the footage, that is, they did it quite often when we weren't looking at the astronauts. And here we have examples. While we're watching the astronauts move around, they changed the frames per second for various reasons. And quite often, early on, they did it whenever an astronaut came close to the camera. And you saw earlier when I disclosed the frames per second that they used. They didn't slow them down as much when they were close to the camera or doing detailed actions because they were they looked too ridiculous. So they had to look to make it normal, as if they were behaving more normal with their hands. For instance, when they got away further from the camera, they got away with more. But as they ran to the camera, for some reason, they thought they should be moving faster when they got close to the camera. So they did a lot of that, and sometimes they did it oddly. I'm not sure why they made the decisions that they made, but they did. They thought it was necessary to fool us, and they were right. Although I think one of the reasons that they succeeded so far for the last 50 years is that no one has fully analyzed the footage as I have. For the most part, it's been accessed, but thanks to the internet, I had access. I found it, and I decided to look at all of it, and what I found was amazing. And we are going through all of these events. If you watch the factor at the bottom of the footage, you can see it change midstream. Sometimes they are significant and sometimes they're not. I'm showing you all the ones that I found. However, during the presentation reveal, I will only show the most significant ones. Here you can see A15 in the winner of this one. You can see I eliminate most of them because you lack motion blur, so here's their version. Look how fast he's going. So down here he slows down. And my assumption is, as they were watching the footage, when they generated it, they said, he just looks too slow in the camera, we gotta speed him up. Here it is at my 0.45 factor, and I was analyzing the footage. I said, whoop, why does he look like a clown? Here's the same trick again. More than a few times, they thought it was necessary. There, it's hardly noticeable. Of course, you speed up the footage and, whoa! He starts out slow, and then he just takes off. There's that stuttery look again, somehow going back in time, and forward again. I don't think that happened in any legitimate footage, ever in the history of footage, except for on the moon. And so, I don't notice any changes they did. It's a subtle change in slow motion, but when I was looking at it here, he looked fast. Then I did the adjustment, it looked better. I'm sure I missed many times exactly what the changes are they made. I just did the most obvious ones that looked and stuck out to me. That was a change in the middle. Did you see how the astronaut just sped up in the middle like that? Here, let's watch that again. Watch as the astronaut comes close to the camera, he's in slow motion. And then, keep watching, there, all of a sudden, he just sped up. There he is again. Looks going fast. He seems to go a decent speed, and then, next. So here we are, the standard 0.615 for rover activity, and they change it so he can run away. If you watch closely, you can see little spasms that the astronauts make. That was a spasm if you didn't notice. Here he is in my constant factor. That's the spasm. And then, now you don't even notice it here. It was proper at 6, 0.615 earlier, and he wasn't proper. I had to find the time change as they became standard practice. When they're near the rover, I find the factor that works, and as they get further away with different factors and so forth, so I just took the opportunities to change. so that I follow the most likely. I do not nail it precisely every time, but I did it enough to show that it occurred. The astronaut walks slowly and then speeds up, if you notice. Look how boring this footage is. It's amazing at their moon speed. No wonder no one wants to look at this. You want to go to sleep. Look at the NASA moon footage. Why? Because it's in slow motion. We can't bear to watch it all the time. It's absurd. So, for posterity's sake, let's speed things up a little, shall we? And now, back to NASA speed. So again, my standard way of showing this to you is my determined way that it was the factor that needs to be utilized. There's a speed change, and then I show you the NASA footage. And then I show you the constant factor that I first created and which was revealed. That it wasn't normal, and I had to do speed change adjustments. So once again, let's have a look at this boring rover footage from this angle and watch the astronaut how he speeds up and slows down at times. I'm sorry that I had to show you this footage. I had to go through this process so that it's clear what is going on. Here's the constant factor. Now let's watch this astronaut speed it up. This one, here's an example. There's a speed change between 0.57 and 0.54, not dramatic. But it's a great example of how the astronaut's in full motion. He hits the ground, starts his different stride, some kind of change, and allows them to hide the factor change.